Welcome to part 2 of product design and development, generating product specifications or engineering specifications. In step 4, kind of right room of this house of quality, we will perform benchmarking. Benchmarking is the study of existing product and revealing their strengths and weaknesses. Even if you are developing a brand new product, nothing like it exists, you can still find some similar functionality that exists in current products and compare those with and evaluate their strengths and weaknesses to the customer requirement. Remember that step 4, once you find some products, you compare them to what you developed in step 2, and that was the customer requirements. So you evaluate each of those customer requirements for the current product and go through a scale of 1 to 5. If it doesn't meet at all, it's a 1, you give it a score of 1. If it completely meets that requirement, then you give it a number 5. Kind of looking at our example that we have here, we are looking at this now section. 2 products are mentioned in this example. They give him some fictional names for this purpose of this lecture, Collab and then Deltor. One of them they showed with the solid triangle, one of them is with a solid square. And scale 1 through 5, this is the scoring scale from 1 to 5 exists here. So for each customer requirement, for example, is easy positioning of seat, the Collab get a score of 2. That means the product meets the requirements slightly. And when you get to Deltor, they get a score of 3. That means the product meets the requirements somewhat, and so on. So those are what those symbols mean in this table, and you can go through the table. And some of them you can see they both got a score of 2, and so on, or they both got a score of 3 here, and so on. So this is what that section of the QFD means and those symbols mean for competition and benchmarking. Going to step 5 of the product and generating the engineering specification, which was the whole goal of this lecture and using this method. That's kind of the room under the roof, section 5. We talked about it a little bit, engineering specification, but this is another description of it. The statement of the design problem in terms of parameters that can be measured and have target values. That measure is an important aspect of it. When we talked about the car door that could be easily open or easily closed, that's not very measurable. But when you put a 40 Newton pound attached to it, something with a unit that you can measure, that's now an engineering specification. This also, these engineering specifications serves as a vision of the ideal product and how to use the criteria, these criteria for your design decisions, and how design decisions affect the customer perception of the quality of the product. So these are very important in product development context. These are the parameters that tell us how we know if customer requirement have been met or not. Again, because it's measurable. That's very important. Your job is to try to find as many engineering parameters as possible that indicate a level of achievement for customer requirements. And they always have to have a set of units attached to them. This arrows that I kind of made down bottom. These parameters that I mentioned, try to find as many parameters and as many engineering parameters that you have. You eventually turn them into design targets. And that's what you go and design based off of. And we'll talk about the difference between design target and engineering specifications. You had a questionnaire that you filled out and voice of customer. By doing this step 5, you turn that into voice of the engineer. If you look at the example that we had here in this lecture, I've kind of enlarged it a little bit. They, for those sets of customer requirements that they had, they kind of come up with these sets of specifications that they have listed here. Seat width, steps to adjust. So pay attention that everything is measurable. Seat width, steps to adjust, force to adjust, force to slide, lifting force, and so on, push force. So they're all measurable. They all have a unit. Number of steps, mostly newtons, because a lot of them are forces. Seconds, a lot of them, again, forces. So they all have a measure. And then you also see an arrow pointing up or pointing down. This helps the engineer to know whether they want this to be high or low number, which one is desired. So that's what these arrows mean. Arrow pointing up, that means a larger number is desired, a lower number or a smaller number is desired, and so on, to kind of keep an eye on what needs to be done. I've listed some engineering specifications here. You can use some of these if you are trying to develop some specifications for your product and for your project. Maybe some of these can inspire you to come up with a good sets of engineering specifications, and so on. Also, I gave you an example up top of, hey, if a customer says something, it's easy to attach, what can you develop for it? And here are some, for example, 4 engineering specifications that you can develop for that easy to attach customer requirement. Next, we're going to move to the main body of this table and all those symbols that you are seeing on your example, the center portion of the house of quality. This is kind of sometimes done in parallel to step 5 to kind of yield additional knowledge and give you a deeper understanding of the product. So you compare each engineering specification to each of customer requirement and see how strong the relation between them is. Not every customer requirement and engineering specifications are going to be related, but hopefully some of them are. If it's a very strong relation, then you put this symbol in it. It's a solid circle, kind of, and it gets a score of 9. A hollow or just a regular circle gets a score of 3. A triangle is 1. And if you just leave it blank, means there is no relation between them. If you want to look at the example that we have here, so steps to adjust height, for example, has a strong relation to easy positioning of seat height. That means this engineering specification and maybe the next one were developed for this customer requirement. And if you come down, they also address other customer requirements. Bottom 2 maybe are not the strongest relationship. So you can go through the list and kind of identify. One problem that I see here, for example, this good lifting position, this one right here, when I go through it, it only has kind of a medium relationship with one of the engineering specifications. It's just right here. It doesn't have any strong relationship with another engineering specification. This is a problem. So that means maybe it wasn't well understood, or maybe it wasn't not well thought through. And when I look at it, maybe good lifting position maybe is not well defined. So you can go back to step 2 and a step 3 and kind of look at it and see if you can revise it or maybe better understand it. The goal for us is that every customer requirement should have at least one specification with a strong relationship. And that was a problem, as you saw in the example. Also, hopefully each specification should measure more than one customer requirement. And if there aren't, then you got to go back, revise it, and kind of maybe understand it better. Step 7 has three kind of sub steps that comes with it. The first thing is, once you have those relationships, what you put in, the scores, then you go back and look at your weights. The example we have here for easy positioning of seat height, minimum time to transfer, easy position of seat height, medium effort, and minimum transfer time, we have scores. The rest are blank. So this is just a multiple and figure out their sum. For the passenger, again, 9 multiplied by 4 plus 321 plus 95 plus 315 and 15, you find the total. All of the specifications for passenger has yielded 1475 if you go through your example and do all the sums based on the scores. And the normalized value, 135 divided by 1475, is 9%. Hold on to this and we'll see it in the example when I kind of show the enlarge, or if you are following along with the example, you will see for that specification, you see a score of 9 on the basement of the house of quality. Same with the agent. Again, same kind of multiple, sum, and normalized value. And on the bottom you see the number 13 for the agent. So you can go through the rest of the columns, do some calculation, check the numbers. For example, for a specification, forced to adjust, we have 8 for the passenger, we have 11% for the agent, and so on. The second part of it, part of this, is do the same thing for competition. What you did in step 4 for the Colab and Deltor, you got to do the same thing for your competition and figure out how much, again, their engineering specification, how strong engineering specifications are in relation to customer requirement. Once you figure that out, then you develop sets of specifications. You develop, sets of design targets for your engineering specifications. So you can refine and kind of adjust your design targets later on, but let's talk about what does design target means and what's the difference between a design target and engineering specification. Here's an example. You want to buy a new camera and you have 2 specifications and they are just a set of specification. It should be less than $300 and it should have 7.2 megapixels resolution. When you look at all of the choices I mentioned here, the 5 choices, some of them are less than 300. No, actually none of them are less than 300. Are some of them at least 7.2 megapixels? Some of them are, but then you don't meet the price requirement. So none of these meets your requirement. If you have a very solid sets of engineering specifications, you go to the market and come back empty-handed. Now we're gonna go kind of sets a design target. Okay, so we give ourselves a range. We say, hey, kind of maybe have it less than or equal to 315 and have at least 7.2 megapixels. We say, hey, our goal, our delighted target is 300. Okay, but because I don't like to come back empty-handed, I'd rather have a camera, spend a little bit maybe more and have a camera, I'm willing to go up to 315. So the lighted target, the green one, is the actual design target that you want to meet. But again, because of how markets are, because how engineering design works, you give yourself a little bit of flexibility, a little bit of a room that close to that delighted target, but again, you still accept it. Beyond that, your design is unacceptable. So if you go above 315, this is rejected. Same thing with design targets. So again, you put out a range. You have an actual design target that you like to meet, but you gave yourself a little bit of flexibility, a little bit of a threshold that helps you do that. So in this case, now when you go to market, there are at least 3 options available for you, and then you can select. Maybe this one is a better option because it's closer to your delighted target. The bottom of the house of quality basement, you can follow up and you follow with me and look at the numbers. We talked about this 9 and 13 throughout the examples. We talked about the competition strength, and then you can see that kind of they set a design target for each of those engineering specifications and so on. So there is a delighted target. So these are the actual target they would like to meet. This is what they're going for. But in some of them, you can see they give themselves a little bit of room that, hey, if we go up to 4, that's okay, but beyond 4, this product is rejected, and so on. And then kind of looking back at the last step, or the roof of the house of the quality, and that's referred to the trade-off. Trade-off is when you kind of want to improve one of your qualities, but it's negatively affecting another one. Trade-off is when 2 separate engineering specifications, they contradict each other. And that's what this section of the house will address. In an ideal world, we want all the specification to be totally independent of each other, but that usually doesn't happen because of trade-off in engineering specifications. So in this case, you look at only engineering specifications, looking at the example that we have. For example, steps to adjust seat height. It has a strong relation with force to adjust the seat. Also has a strong relation with this one, with time to transfer between seats. Another example, force to slide 95% male passengers, has a medium relationship to this one. Means when you want to improve another one, you are going to affect the other one as well. Has another medium relationship with another spec 2 so far. So ideally, you want this to be less crowded, or at least not have too many strong relationships, because then what happens is they call your design gets stuck. You can't design because there are too many interdependence between your engineering specifications. If that happens, you got to go revisit some of your specification and some of your customer requirements. Maybe you didn't understand some of them well. What I see here is totally fine, totally normal. Maybe this one will cause you some trouble a little bit because it has a strong relation with two of the other specifications. But again, ideally you want it to be less crowded. Here's another way of showing it. This is the exact same thing, but especially if you're using Excel, it could be shown this way. They're using different symbols, plus, minuses, and question mark, and so on. If the relationship is not clear, that means one of your specifications are not clear. So you can go back again and kind of revisit it and understand, maybe define it further, or revisit some of your description of customer requirements or your engineering specifications. In the last slide, self-read, I included a little bit of a reading about, kind of a little bit about customer requirements and about benchmarking. It's a good read. Please feel free to pause the video and read these slides. But this is the end of generating engineering specifications. Thank you.